Welcome everyone. Today we move into one of the most influential ideas in modern deep learning, Generative Adversarial Networks, or GANs. This lecture sits within our broader treatment of deep generative modeling, and the goal is not only to see what GANs can produce, but to understand from an engineering perspective why they work and where they fail. We will build up from generative modeling in general, through autoencoders and variational autoencoders, and then arrive at the adversarial framework that gives GANs their name. Along the way, we will cover the generator and discriminator, the minimax objective, the latent noise vector, training dynamics and instability, mode collapse, architectural variants like DCGAN, progressive GANs, pix2pix, CycleGAN, conditional GANs, and style transfer. And finally, the medical and global health applications that make all of this relevant to our course. Let us begin by placing GANs in context. Here we are, reminded that deep learning is more than convolutional and recurrent networks. It shows a panel of architectures: graph convolutional networks, GCNs, network embedding, and knowledge, graph embedding, NEKGE, autoencoders, AEs, deep neural networks, DNNs, recurrent neural networks, RNNs, and convolutional neural networks, CNNs. At the center is a diagram connecting disease, target, and drug, which reflects the drug discovery and biomedical framing of this figure from Pan in 2022. The key message is that different data structures and different goals call for different architectures, and generative models are one important branch we have not yet explored deeply. Generative modeling is a distinct paradigm from the discriminative models we have mostly studied so far. Discriminative models learn a boundary or a mapping from inputs to labels, while generative models try to learn the underlying data distribution itself, so that we can sample entirely new, realistic examples. Now we consider a provocative question. Which image is fake? It shows 4 highly realistic human faces labeled A, B, C, and D. Pause the video and take a minute to think about your answer. Interestingly, none of these faces were ever actually physically photographed. They were all synthesized by a generative model, and to be honest, it is very hard for a human to tell. And as many of you already know, this is not even the current state of the art in AI-generated content realism. This is the perceptual power that GANs and related models brought to computer vision, and it sets up both the promise and the ethical concerns of synthetic media. The same challenge returns here, but in a medical context. Which of these dermatology images is fake? It shows 4 dermoscopic images of pigmented skin lesions labeled A through D. Take another minute to think about your answer. Turns out all of them are real. Surprised? Well, actually that was a lie. They are all synthetically generated. Or maybe they are actually real. Can you even tell? The issue is that the resemblance of synthetic with real dermoscopic images is already outstanding. The lesson ultimately is that synthetic generation is not limited to faces. It extends to clinically meaningful images such as dermoscopy, radiology, and histopathology. That capability is exactly what makes generative models attractive for medical data augmentation, and simultaneously what makes validation and provenance so important in health settings. Let's now formalize what generative modeling is trying to do. The central question is, how can we learn P model of X that is similar to P data of X? On the left is a density function estimation cartoon, showing a smooth probability density over a one-dimensional space, with samples clustered under the peaks. On the right, the same idea is shown with images. Input samples drawn from the true data distribution, P data of X, and generated samples drawn from the learned model, distribution P model of X. The stated goal is to take training samples X from some distribution and learn a model that continuously represents that distribution, so we can both evaluate density and draw new samples. A more formal, less unidimensional way of visualizing this can be understood as the search of a generative model, that given a modulated unit, Gaussian input is able to generate a distribution of samples in the same space as the true data distribution, in this case image space, so that the loss or accumulated errors between the true data distribution and the newly generated distribution is minimized. This essentially sets up the motivation for why we build these architectures in the first place. So why would one want to use generative models? Well, there are at least 2 complementary motivations: to uncover underlying features in data, or to detect outliers, or map data distributions. On the left, we see an example of uncovering underlying data features, where we see grids of faces varying in color, pose, and illumination, illustrating that generative models can learn the latent factors of variation in a dataset. On the right, we see some examples of what detecting outliers and map data distributions means. Here, there is a bell curve, where 95% of driving data is common cases for a self-driving car application, sunny, highway, straight road, while the tails contain edge cases, like an airplane on the road, harsh weather, and pedestrians. The point is that by modeling the full distribution, we can identify where data is dense and where it is sparse, which helps us find rare and dangerous cases. The closing line is important for our course. This information can be used to help create fair and representative datasets, which directly connects generative modeling to equity in global health. Next, latent variable models are introduced as the umbrella for what follows. On the left, it shows autoencoders and variational autoencoders, drawn as an encoder that compresses an input into a latent code, followed by a decoder that reconstructs an output. On the right, it shows generative adversarial networks, with a generator that maps a latent input into a synthetic sample, and a discriminator that compares real samples against generated ones. So both families rely on a latent representation, but they differ fundamentally in how they are trained. Autoencoders reconstruct, while GANs compete. Let's look at what a latent variable actually is, using the allegory of Plato's cave. It depicts prisoners chained facing a wall, seeing only the shadows cast by objects and the fire behind them. The analogy is that the true underlying causes, the real objects, are hidden, and we only observe their projections, the shadows. A latent variable is exactly this, an unobserved factor that generates the observable data, and much of generative modeling is about inferring and manipulating those hidden factors. Now we introduce autoencoders concretely, asking how can one learn such a latent space. It shows a handwritten digit, the input X, passed through encoder layers down to a compact latent code Z, then through decoder layers to a reconstructed output X hat. The idea, as the text explains, is to train a compression and decompression that attempts to reconstruct the original image. Surprisingly, this works, and it often yields a decoder that maps from the latent space back to the reconstructed input space, giving us automatic encoding of data. Note that the reconstructed digit on the right looks blurrier than the input, which foreshadows a recurring theme. Reconstruction is rarely perfect. Focusing now on the encoder half of an autoencoder. The encoder learns a mapping from the input data X to a lower dimensional latent space Z. The bullets highlight that learning is done in an unsupervised approach, that what is learned are lower dimensional features, and that this latent space is a form of representation that can be obtained from both unlabeled and labeled data. This unsupervised feature learning property is one of the main reasons autoencoders are so useful as a building block. Turning to the decoder half. The decoder is described as a mirror network that learns how to take a set of input features in latent space form and reconstruct an output in the input space. Conceptually, the decoder maps the latent Z to a reconstruction X hat. The second bullet notes that the decoder makes unsupervised training possible, and is often the most useful part of the architecture in downstream applications, because it is what actually generates data. The bottom line reminds us that reconstruction may not be perfect, which is a limitation we will keep returning to. Here we see how autoencoders are trained. The full pipeline is shown again. Input X, encoder, latent Z, decoder, reconstructed X hat, and at the bottom is the loss function. The loss is the squared reconstruction error, written as loss of X and X hat equals the norm of X minus X hat squared. In other words, we push the reconstruction to match the input as closely as possible, and gradients flow back through both decoder and encoder. This slide illustrates the trade-off between the dimensionality of the latent space and reconstruction quality. It shows 3 grids of reconstructed digits, a 2-dimensional latent space, a 5-dimensional latent space, and the ground truth. The 2-dimensional reconstructions are noticeably degraded. The 5-dimensional ones are much closer to ground truth. The takeaway, printed on the slide, is that autoencoding is a form of compression, and the smaller the latent space, the larger the training bottleneck. There is a tension here. Too small a latent space loses information, while too large a latent space can memorize rather than generalize. Now let's move on to the concept of variational autoencoders, or VAEs. VAEs are the probabilistic evolution of autoencoders, and they are the conceptual bridge toward generative sampling. Let's look at the key difference between a VAE and a traditional autoencoder. Variational autoencoders are probabilistic versions of traditional autoencoders, and the idea is to sample from a mean and a standard deviation to compute a latent space. The diagram shows the encoder computing a distribution, written here as p phi of z given x, producing a mean vector mu, and a standard deviation vector sigma, from which z is sampled, and then a decoder computing q theta of x given z. The loss at the bottom has 2 terms, a reconstruction loss, the norm of x minus x hat squared, plus a regularization term, a divergence d between the inferred latent distribution, p phi of z given x and a prior p of z. So instead of encoding a single point, the VAE encodes a distribution over the latent space, which is what allows smooth sampling and generation. Here we discuss the priors placed on the latent distribution of VAEs. On the right is the KL-divergence, the divergence between distributions, written explicitly as -1/2 times the sum, over dimensions of sigma j plus muj squared minus 1 minus log sigma j. Here p/phi of z, given x, is the inferred latent distribution, and p of z is the prior on the latent distribution. The slide emphasizes that the choice of prior is important, and a common choice is a standard normal, p of z equal to a normal distribution, with mean 0 and variance 1. The two bullets explain why. This prior forces the encodings to distribute evenly around the average of the latent space, and it penalizes the network when it tries to cheat by clustering points around specific regions, which is essentially data memorization. The scatter plot on the left shows the resulting latent space, a roughly circular cloud of colored points corresponding to different classes, mixed together around the origin. Consider now the central technical problem in training VAEs. The problem, in red, is that we cannot backpropagate gradients through sampling layers because a random sampling operation is not easily differentiable. The diagram highlights that the step where we draw SA from the mean and standard deviation is a sampling event, and we never have access to the real distribution, only samples from it. This is a genuine obstacle. Gradient descent needs a differentiable path from the loss back to the encoder parameters, and naive sampling breaks that path. The solution to that problem is the reparameterization trick. Instead of directly sampling z from a normal distribution with mean mu and variance sigma squared, we rewrite the sampled latent vector as a sum of a fixed mu vector plus a fixed sigma vector scaled by an independent random constant epsilon, drawn from a standard normal, a normal with mean 0 and variance 1. This is written as z equals mu plus sigma element-wise multiplied by epsilon. The elegance is that the randomness is now isolated in epsilon, which does not depend on the parameters, so gradients can flow through mu and sigma, while the stochasticity is pushed to an external input. Here the reparameterization of the sampling layer is formalized as a computation graph. On the left is a legend. Blue squares are deterministic nodes and green circles are stochastic nodes. The original graph shows z drawn stochastically from p phi of z given x, feeding into a function f, which blocks backpropagation through the stochastic node. The reparameterized graph rewrites is_d as a deterministic function, g of phi, x, and epsilon, with epsilon drawn externally from a standard normal, so that backpropagation can compute the partial of f with respect to z and with respect to phi. This is the mathematical machinery that makes end-to-end training of VAEs possible. Take a look at a compelling application of VAEs, latent perturbation. The idea is to smoothly change, increase or decrease a single latent feature, while keeping the others fixed. The strip of faces shows the head position rotating smoothly from left to right as one latent dimension is swept. The takeaway is that different dimensions in the latent space Z can be interpreted as encoding meaningful latent features, in this case head pose. What we're looking at here is a latent perturbation demo. On the left are sliders corresponding to individual latent dimensions, with numeric values feeding a decoder that produces a reconstructed image, here an 8. On the right is a grid of generated digits from 0 through 9. As you move each slider, the reconstructed image changes continuously, demonstrating that the latent space is smooth and navigable. The slide references a live demo hosted at ciares.com for hands-on exploration. As I am showing here, you can go into this demo and explore intuitively how slider movement, which is akin to modulation of hidden variables in the latent space, can be performed smoothly. Each of those sliders could, for example, correspond to roundness or closeness, and the fact we can access this and modulate it is a very interesting property, particularly in biological systems and medical presentations where a prior of smoothness holds. Now we connect latent perturbation directly to fairness and bias mitigation. The idea, stated on the slide, is to try to mitigate bias in various image datasets through learned latent structures. The workflow on the right has 2 steps. First, learn latent features and estimate their distributions. Second, quantify and fix bias by adjusting the distribution. The mechanism is to adjust the latent distributions, essentially flattening them, to create more inclusive and fair datasets, so that underrepresented groups in the tails are sampled more often. This is a direct technical route from generative modeling to equitable AI, which is a core theme of this course. Next up is latent variable mapping and the concept of disentanglement. The grid of faces varies head position along one axis and smile along another, showing that two separate latent dimensions independently control two interpretable attributes. The text explains that it is ideal if latent variables after training are mostly uncorrelated with each other, essentially behaving like principal components. A way of forcing variable independence is by fixing a diagonal prior on the latent variables, and this process is called disentanglement. Disentangled representations are easier to interpret and manipulate, which matters for both scientific understanding and controllable generation. Here we see beta VAEs, an extension designed to encourage latent space disentanglement. It compares a standard VAE, where beta equals 1, against a beta VAE with beta equal to 250. The beta VAE loss is written as the expectation under the inferred posterior of the log likelihood, the reconstruction term, minus beta times the KL-divergence between the inferred posterior and the prior, the regularization term. The slide notes that beta greater than 1 imposes a latent bottleneck constraint to encourage efficient latent encoding with disentanglement. Visually, the beta VAE faces vary more smoothly and along cleaner attribute axes, at some cost to raw reconstruction fidelity, which is the classic disentanglement versus reconstruction trade-off. We now turn to the heart of the lecture: Generative Adversarial Networks, or GANs. Everything before this has built the intuition of latent variables and generation. Now, we introduce the adversarial framing. Let's ask what happens if we want to generate a new sample. The approach described is that we sample from a simple input, noise, which is then decoded by a network that has learned a transformation from the training distribution. The diagram shows a noise vector C entering a generator network, labeled G and described as a decoder, which outputs X hat fake. That output is an AI-generated sample from the training distribution. This is the generator in isolation. The missing ingredient, the training signal, is what the adversarial setup provides. Here's the canonical GAN architecture. On the left, the generator, labeled G, turns an input, usually noise C, into a new sample X hat synthetic, in an attempt to trick the discriminator. On the right, the discriminator, labeled D, receives either a real sample, X hat real, or the generated X hat synthetic, and its goal is to identify synthetic, fake, data created by the generator from real data collected from the real world. The discriminator outputs a scalar Y, essentially the probability that the input is real. So we have two networks locked in competition, one forging, one detecting. The figure here gives an intuitive picture of the adversarial loop from Laura Martinez-Malera in 2021. A real-world image is drawn from the training set and fed to the discriminator, while random noise is fed to the generator to produce a fake image, here a distorted dog. The discriminator, a CNN, then classifies each image as real or fake, shown as a green or red light. The dotted feedback arrows indicate that the errors are used to update both the generator and the discriminator, so both improve over successive rounds. This is the core training loop we will now unpack step by step. We now begin a 6-step intuition sequence for GANs. Step 1. The generator takes a noise input to create synthetic data, shown as yellow dots placed along a one-dimensional number line. At this early stage, the synthetic data is essentially arbitrary, scattered without regard to where the real data lives. On to step 2. The discriminator now analyzes both real and synthetic data made by the generator to learn how to differentiate them. Green dots represent real data and yellow dots represent synthetic data, placed on the discriminator's number line. The discriminator's job is to find the pattern that separates the two populations. Moving on to step 3, first version. The discriminator predicts the probability of being real data over many samples, shown as a dashed line at P of real equals 1. At this point, the discriminator is learning a probability function across the input space, higher where data looks real and lower where it looks fake. Step 3 continues here by adding the probability profile. Gray bars now rise above the real, green, data points, indicating the discriminator assigns high probability of being real to those regions, and lower probability to the yellow synthetic points. This visualizes the discriminator's learned decision surface. It has figured out where the real data concentrates. Sharpening step 3 further, the gray probability bars now peak tightly over the cluster of real green data points, and are low over the synthetic yellow points on the left and right. The discriminator has become confident. It strongly believes the central region is real, and the outer synthetic points are fake. On to step 4, now the generator tries to improve, making more realistic synthetic data. On the generator's number line, the yellow synthetic points have shifted inward, moving toward the region where the real green data lives. The generator is learning to place its samples where the discriminator thinks real data should be. Step 4 continues. The generator has moved even more of its synthetic yellow points into the neighborhood of the real green cluster. The two distributions are starting to overlap, which is exactly the goal. The generator wants its samples to be indistinguishable from real data. Step 4 is now fully advanced. The synthetic yellow points are now interleaved closely with the real green points, tightly co-located in the central region. The generator's distribution is beginning to match the real data distribution. Moving on to step 5. The discriminator now tries to predict again what is real versus synthetic data, given the generator's improved samples. Because real and synthetic points are now overlapping, the discriminator's probability bars are broader and less discriminating. Its previously sharp confidence is eroding. Step 5 continues. The discriminator's probability profile is now more spread out and less peaked, reflecting growing uncertainty. When the generator's samples sit right on top of the real data, the discriminator can no longer cleanly separate them, and its accuracy approaches random guessing. Finally, step 6. The generator tries to improve even further, producing even more realistic synthetic data, and the yellow and green points are now almost perfectly intermixed in a tight cluster. This is the approach to the ideal outcome, where the generated distribution matches the real distribution so well that the discriminator cannot tell them apart. This is the intuitive picture of the Nash equilibrium of the game, where neither network can unilaterally improve. Now we formalize that intuition into the GAN training objective. The discriminator learns to predict real versus synthetic by maximizing d of x toward 1 for real data and minimizing d of g of z toward 0 for generated data, while the generator learns to make realistic synthetic data by maximizing d of g of z toward 1. At the bottom is the full minimax objective. Minimize over the generator parameters theta g, maximize over the discriminator parameters theta d of the expectation over real data of log d of x, plus the expectation over the latent prior of log of 1 minus d of g of z. This is described as the min-max game, or loss. The discriminator maximizes this value function, pushing correct classifications up, while the generator minimizes it, trying to fool the discriminator. The equilibrium of this two-player game is where the generated distribution equals the data distribution. Let's ask why GANs, by contrasting them with traditional maximum likelihood approaches. On the left, the traditional maximum likelihood approach produces a broad blurry blue band around the data manifold, indicating it spreads probability mass and tends to average over modes. On the right, the GAN produces a sharp, thin blue curve that hugs the data manifold much more tightly. The visual message is that GANs can capture sharp, high-fidelity structure that likelihood-based methods often smear out, which is why GAN samples tend to look crisper and more realistic. Here we see how, after training, we actually generate new data with GANs. The discriminator half is now faded out, and the point, in text, is that after model training, we can use the generator network alone to create new realistic synthetic data. We simply feed fresh noise vector Z into the trained generator G, and it produces novel synthetic samples X hat synthetic. The discriminator was scaffolding for training. At inference time, only the generator is needed. Considering why we would use GANs in the first place, the slide gives two deeper motivations. On the left, under generating fake data, a refiner network R takes synthetic eye images and refines them to look like unlabeled real images, improving realism of simulated data. On the right, under cannot formulate loss, a face editing example shows attributes like blonde hair, gender, aged, and pale skin being manipulated. The insight is subtle but important. For many perceptual tasks, we cannot write down an explicit pixel-level loss that captures realism, so the discriminator effectively learns the loss function for us. That is a major reason GANs succeeded, where handcrafted objectives failed. Here's the standard GAN-CNN architecture, the design pattern popularized by DCGAN, cited here from Hayashi and colleagues in 2019. The generator on the left starts from the latent vector C and uses a series of fractionally strided convolutions, sometimes called transposed or deconvolutions, expanding spatial resolution from 4 by 4 up through 8, 16, 32, and 64, while reducing channel depth from 512 down to 3 color channels. The discriminator on the right is a mirror image, a standard convolutional network with stride 2 convolutions that progressively downsample the image from 64 by 64 while increasing channel depth from 64 up to 512, ending in a real versus fake decision. The key engineering ideas of this DCGAN style design are strided and fractionally strided. Convolutions, instead of pooling, batch normalization, and no fully connected hidden layers, which together stabilize training. Turning to the progressive growing of GANs, or PGAN, from NVIDIA in 2022. The core idea is to grow both the generator and discriminator progressively during training. Start by generating tiny 4x4 images, then add layers to reach 8x8, then 16, and so on, up to 1024 by 1024. Both networks are trained in lockstep, with the real images downsampled to match the current resolution. This curriculum, from coarse to fine, dramatically stabilizes training of high-resolution GANs and yields the strikingly realistic faces shown on the right. Here are the progressive growing GAN results, a gallery of high-resolution synthetic human faces. These faces are entirely generated, yet they exhibit realistic skin texture, hair, lighting, and facial structure. This is the kind of output that made the which image is fake question at the start of the lecture so difficult to answer. Now we see progressive growing GAN results in a medical context, dermoscopic skin lesion images, citing Bisotto and colleagues in 2019. These are synthetic dermoscopy images of pigmented lesions, generated to look like real clinical dermoscopy. This directly demonstrates the medical relevance. High-quality synthetic lesion images can augment dermatology datasets, which is especially valuable when real labeled data is scarce or imbalanced across skin tones. This diagram details the architecture behind those synthetic lesion results, again from Bisotto and colleagues in 2019. The pipeline takes a semantic mask, passes it through a generator G, and produces synthetic lesion images that are compared against real ones by multiple discriminators D1, D2, and D3 operating at different scales. On the right, the residual block, downsample, and upsample building blocks are spelled out, using convolutions, batch normalization written as BN, and the ReLU activations. The generator G is a deep stack of a 7x7 convolution, downsampling blocks, a series of residual blocks, upsampling blocks, and a final TANH activation, while the discriminator D uses strided convolutions with leaky ReLU activations. This multi-scale conditional residual design is what enables realistic, controllable medical image synthesis. This transitional results slide shows progression from 2016 to 2019, contrasting synthetic samples against a real sample, citing Bisotto and colleagues in 2019. The message is the rapid maturation of GAN image quality over just a few years, from crude early outputs to samples nearly indistinguishable from real clinical images. Next, we introduce image-to-image translation with Pix2, Pix. The input can be noise, a sketch, or another image. Here, a line drawing of a cat, and Pix2 Pix translates it into a realistic output image, a photorealistic cat. Pix2 Pix is a conditional GAN for paired image translation, where the generator maps an input image to an output image, and the discriminator judges whether an input-output pair looks real. This enables applications like turning sketches into photos, maps into satellite views, or segmentation masks into realistic scenes. Turning to CycleGAN and domain transformation. CycleGANs can learn transformations across domains with unpaired data, which is a major practical advantage, because paired training examples are often unavailable. The diagram shows two domains X and Y, with a generator G mapping X to Y, and a generator F mapping Y back to X, along with discriminators DX and DY for each domain. The classic example shown is translating a photo of a horse into a zebra and back, learning the mapping without ever seeing matched horse-zebra pairs. Let's look at the mechanism that makes CycleGAN work, cycle consistency loss. The top diagrams show that if we map X forward with G to get Y I hat, then map it back with F, we should recover the original X and symmetrically for Y. The cycle consistency loss penalizes the difference between the original and the round-trip reconstruction in both directions. As the caption explains, this encourages one-to-one mappings, thus preventing many-to-one mappings that cause mode collapse. This is a crucial point. Cycle consistency is a structural constraint that combats one of the most notorious failure modes of GANs, where the generator collapses to producing only a few outputs. Now we introduce the conditioning GAN, also known as the conditional GAN or CGAN. Sometimes we want to control the nature of the output using a conditioning label. Here a conditioning factor, labeled C, is fed into both the generator alongside the noise Z, and into the discriminator alongside the real or synthetic image. By conditioning on C, we can direct the generator to produce a specific class or attribute, for example a particular digit, a particular disease category, or a particular imaging modality. Conditioning turns an unconstrained generator into a controllable one which is essential for practical targeted data generation. Here is a landmark medical application, synthetic data in machine learning for medicine and healthcare, a Nature Biomedical Engineering comment by Chen, Liu, Chen, Williamson, and Mahmood, published June 15, 2021. The figure compares synthetic and real images across skin lesions, chest X-rays, and renal cell carcinoma histology, including chromophobe, clear cell, and papillary subtypes. The bottom bar charts compare downstream classifier performance, measured by AUC, when training on real data alone, versus real plus synthetic data. The message is that adding GAN-generated synthetic data can improve model performance, and importantly, it offers a route to privacy-preserving data sharing, since synthetic images need not correspond to any real patient. This is a central argument for GANs in global health, augmenting scarce data and sharing it without exposing protected patient information. Now, before we conclude this session, I wanted to put forward an interesting and potentially provocative use case of GANs to improve skin of color representation in medical datasets, particularly dermatology. As many of you may know, there are a variety of systemic biases that have permeated the practice of medicine for decades. One critical one is that the quantity and diversity of textbook images of skin diseases variants across a wide range of population types, particularly in darker skin, remains lacking. While ideally data collection in these populations is necessary and would be critical in addressing these biases, a possible method to supplement this could be the use of domain transfer techniques and GANs to create synthetic and semi-synthetic samples for dermatology in skin of color, of course assuming that its presentation remains consistent, which is actually not necessarily true across dermatological diseases, particularly those with autoimmune origin. Here, original content image, a face with acne lesions on lighter skin, is combined with a style image, capturing a different skin tone, to produce a stylized image that preserves the lesions but shifts the skin appearance. This kind of style transfer could be powerful for global health, because it could lead to the generation clinically consistent images across diverse skin tones, helping to build dermatology models that generalize equitably across populations. This is, of course, but a single simple, and perhaps provocative example, just intended to inspire others to directly address the well-documented problem underrepresent darker skin tones in dermatological datasets, and I encourage each and every one of you to think how you could help address this issue with similar techniques or new ones. Let's now place today's topic within the full course agenda. The broader point is that generative models are one tool among many, and the strongest global health solutions usually combine several methods. Here we list the resources for this lecture. Under bibliography is the paper Attention is All You Need by Vaswani and colleagues. Under software is Google Colab at colab.research.google.com, which is a convenient environment for experimenting with generative models without configuring a local GPU. To summarize today's lecture, generative models learn the data distribution itself, so we can sample new, realistic examples. Autoencoders compress and reconstruct. Variational autoencoders make this probabilistic and enable smooth sampling through the reparameterization trick. And GANs frame generation, as a competition between a generator and a discriminator governed by a minimax objective. The generator maps latent noise into synthetic samples, while the discriminator learns to tell real from fake, and at equilibrium, the generated distribution matches the real one. We saw the practical challenges of adversarial training, including instability and mode collapse, and the architectural and algorithmic responses to them, from DCGAN and progressive growing to cycle consistency, conditioning, PIX2PIX, CycleGAN, and style transfer. Finally, for global health, these methods enable data augmentation, privacy-preserving synthetic data, cross-domain and cross-modality synthesis, and fairer, more representative datasets across diverse populations. Thank you, and see you next time.